First of all,
Roshan, you are so relaxed. I think you completed the portion. I think. That is why.
Okay.
No, sir, not like that. Sir, basically for that quiz 2, 3 and 4, na? Chapter 3 and 4.
Yes.
Roshan, one doubt. Let us.
Please tell me, sir.
Ignition delay with flat piston will be less or
For SI or CI?
CA. Our
CI, it will be maximum, sir. Maximum. It will have maximum delay.
Where?
With the flat piston, the delay will be very high.
Why?
Because there is no secondary motion of the air.
Why do we need to have Tell me, Roshan. Why?
Correct.
You are right only. Just give the.
You have some other idea?
No. Basically, if you have the flat piston, what is happening is like CI is self auto ignition burning mechanism. So if you are not having sufficient air motion, then what will happen is flame choking will happen. So to break the flame choking, you have to have some secondary air motion, which is very sufficient in toroidal type of combustion chamber. But in a flat face like piston, the secondary motion of air after at the TDC, it will be very minimal actually. So hence it is not required to. It is not I would say recommended to have flat piston for the CI.
But still squish will be very high and swirl will be
0
with respect to squish, right?
Squish squish is very helpful for SI engine because it is pushing the charge to what I mean to say is towards the spark plug. Whereas in
Hello, good evening to all of you.
Good evening, sir.
Good evening. Am I audible?
Yes, sir.
Yes, sir.
Okay, fine. Okay, let me start with attendance. I hope my screen is visible to you.
Yes, sir.
Okay, please answer your attendance. Aditya Kumar.
Present, sir.
Anand.
Yes, sir.
Ananta Kumar.
Yes, sir.
Arunachalam.
Yes, sir.
Hasan.
Present, sir.
Hemant. Is he present, Hemant? Okay, he is not there. Jagan.
Yes, sir.
Kesav Prasad.
Yes, sir.
Lakshmi Narayanan.
Present, sir.
Prabhakaran.
Present, sir.
Prem Vinayak.
Yes, sir.
Rahul.
Yes, sir.
Roshan Kumar.
Yes, sir.
Sabish Kumar.
Yes, sir.
Satish Kumar.
Present, sir.
Titus.
Yes, sir.
Malish.
Yes, sir.
Vigneshwaran.
Present, sir.
Vijayaraj.
Yes, sir.
Vikash.
Present, sir.
Vivekanand.
Present, sir.
Yadav.
Yes, sir.
Yuvraj.
Present, sir.
Okay, there is one absentee today, Hemant. Okay, so welcome back to this class on IC engine combustion and pollution. We are in second module now. We are in emission module. Combustion module is done. Now we are in the second module. In the second module, the first chapter is about pollutant formation in SI and CI engine. So we are going to discuss the factors affecting emissions, pollutant emissions from IC engine. So an overview of the content. So here we are discussing about the pollutants that are emitted from the IC engines, SI and CI engine. So we will focus on what type of pollutants are emitted. What are the health effects of these pollutants? Okay, because of the health effects, their concentration is under check. You know, each country have their own emission certification agency. They check or monitor the pollutant levels before an engine, IC engine based vehicle is launched in the market. So it is undergoing a legal compliance, this pollutant concentration. It needs to be monitored because of several health effects they create. I'm going to discuss about that. We will also discuss about the sources of pollutant formation, also mechanism, pollutant formation mechanism. Once you are familiar with the sources and mechanism of pollutants, we can devise a suitable control strategy. Before that, we will also discuss about the various factors, engine design and operating variable that affects or influence the pollutant formation. These are going to be different. These factors are going to be different, and also sources are different for SI and CI engine. So we will deal with them separately. The last class I have provided an overview of. Could you please mute your mic? The last class I have provided an overview of SI and CI engine emission. So we know these emissions from engines, IC engines, are broadly of two categories. One is tailpipe and other one is evaporative emission. Tailpipe and evaporative emission. Okay, so evaporative emission has minimal effect. Okay, generally it is taken care. Only in SI engine, the evaporative emission levels are high because we deal with the high volatile gasoline in spark ignited engine. So because of that, the evaporative emissions are more. And the sources are the vent provided in the tank, carburetor, as well as in the crankcase. Okay. So we have suitable methodology or approach to address this evaporative emission from these three sources in SI engine. CI engine, fuel tank and carburetor vent based emissions won't be there because diesel, you know, it's a heavy fuel, it won't vaporize readily. But crankcase vent will be there through the blow-by source. We have already discussed about that, and it's taken care by recirculating these gases into the intake system. So evaporative emission is not a major issue from IC engine. The problem is with tailpipe emission. So we need to understand this clearly. There are two categories of pollutants that are emitted from the engine tailpipe. In fact, pollutants are nothing but they are the products of combustion, which we have discussed in the first module. We discussed about the combustion phenomena happening in SI and CI engine. As a resultant of this combustion phenomena, various species are produced or generated. They are categorized as product, and some of the products, some of the species are designated as pollutants because of the health effects they create in the human being. There are two broader categories of pollutants as we discussed. One is primary and other one is secondary pollutant. Primary pollutant are the major source for health effects. The primary pollutants also lead to secondary pollutants as indicated here, and there are four species designated as primary or criteria pollutants or regulated pollutants. Okay, these are different nomenclature follow to indicate these pollutants. Unbound hydrocarbon, carbon monoxide, oxides of nitrogen, which include NO and NO2, X is equal to 1 and 2, particulate matter, are simply particulates. So these four are the designated regulated criteria pollutants because their concentration needs to be checked by an emission certification agency. In India, we have ARAI in Pune. They are the legal emission certification agency. So any new vehicle should comply with the concentration of these four pollutants according to the current standards. We follow currently BS6, which is equivalent to Euro 6 from April 2020. Okay, in all the major metropolitan cities in India. So these four species are under check. Okay, they are the levels are under control. They are very low. Later on, we will. In fact, this is one of the major challenge in engine R&D. We need to ensure that the concentration of these four species are very low. It should comply with the legal standards. Secondary pollutants are formed or generated from the primary pollutant. Once the primary pollutants are let out into atmosphere, they also result in forming the secondary pollutant. Two major secondary pollutants are ozone and NO2. Ozone forms due to NO2 reacting with ultraviolet, in presence of ultraviolet radiation from sun. Okay, NO2 form O radical. Radical is an active species which combines with oxygen in the atmosphere and form O3. O3 is ozone. Okay, this is a ground level ozone is a pollutant, designated pollutant. It creates health effects. Ozone in the atmosphere, upper atmosphere is safe, and in fact we need this to prevent UV radiation reaching the earth. But ground level ozone is the pollutant, and ozone in fact react with NO. This is also emitted. This is one of the primary pollutants. So you see that this primary pollutant again react with ozone. Ozone is also will actively participate in chemical reactions. Okay, ozone is an active species. Ozone react with NO and form NO2. NO2 is again a pollutant. So you see the kind of cyclic chain reactions carrying on. Okay, once NO2 levels are increasing in the surrounding ambience, you see that NO2 is getting formed again, and this NO2 leads to forming ozone. So NO2 and ozone levels in the ambient, surrounding ambient start to build up because of these reactions, chemical reactions that are happening around us in the atmosphere under ambient pressure and temperature condition, not even high pressure and high temperature. These chemical reactions are happening under normal or ambient conditions. Okay. And NO2 in presence of volatile organic compound. Volatile organic compound is an unbound hydrocarbon is a complex more than 100 species. Okay, any partially oxidized fuel, you know, we discussed in chapter 1 diesel and gasoline molecular composition. They are complex multi-component mixtures. Okay, the partially oxidized are the species that miss combustion are categorized as a C from the tailpipe. So you have various unborn species coming out of the tailpipe. Okay, and among them, some are designated as volatile organic compound. This volatile organic compound react with NO2 and form this smog. Smog will obstruct the visibility on the ground level. Under certain conditions, you would have observed on the road that there is a smog. Okay, conditions. Okay, it is an indication that the NO2 level in the surrounding ambience is high along with the volatile organic compound. So with this, today I'm going to start with the typical levels of pollutants emitted from SI and CI engines. We will just look at some numbers. What are the typical values of these pollutants emitted from SI and CI engine? In a spark ignited engine, you have 3 major pollutants out of 4 we discussed just now as primary pollutant. One is NOx. NOx is NO and NO2. Out of this, NO levels are very high from SI engine. It's around 97% in general. NO2, nitrogen dioxide, its level is generally low, very low in SI engine. We generally ignore this NO2. Okay, you can see that it is 3% or less than 3%. Later on, I will discuss, when we discuss about the mechanism of pollutant formation, I will discuss why NO2 levels are less and NO levels are high in SI engine. These are the typical numbers. The NOx concentration, that is primarily NO, will be around 20 grams per kg of fuel that is burnt in the SI engine. Okay, this unit is gram per kg of fuel burnt. 20 grams of NOx is emitted from the spark ignited engine for every kg of fuel that is burned. So this much of NOx levels are added to the surrounding ambience right by burning each kg of the fuel in a spark ignited engine. Unburned hydrocarbon, the levels are around 25 grams per kg of fuel that is burned. CO, carbon monoxide, it's high. You could see that it's around 200 grams per every kg of fuel that is burnt in a SI engine. This may vary based on engine type and operating condition, but these are some typical numbers to get the feel of how much of pollutant concentration is emitted from spark ignited engine. As you can see, there is no particulate emission from spark ignited engine. You have only these 3 primary pollutant, NOx, SC and CO, out of which NOx include primarily NO, not NO2. Okay, NO2 is negligible. Why there is no particulate emission from SI engine?
Because of homogeneous mixture of fuel and air.
Yeah, so we have a homogeneous mixture combustion in spark ignited engines. So we have a homogeneous mixture. And what is the typical operating fee we discussed for SI engine?
It's basically 0.8 to 1.2.
0.8 is rare. Generally, it starts from 0.9. It may go up to 1.2. Okay, this is the operating fee range. Okay, so the thing is, since we have a homogeneous mixture, this concentration fee value is around this number, 0.9 to 1.2 everywhere. So you have a homogeneous fuel-air mixture distribution in spark ignited engine with a fee in the range of 0.9 to 1.2. Okay, to form, so particulate matter consists of different substances. In fact, all three states of matter will be there in particulate: solid matter, which is soot; liquid matter, which is unburned fuel and lube oil; also gaseous substances. Okay, so for example, sulfur oxides and nitrogen oxides. Everything put together is particulate matter. Okay. Soot is a primary component of particulate matter, and soot, which is a primary component of particulate matter, forms with rich mixture. What is rich mixture?
More than 1, sir, actually.
Phi greater than 1. So when phi is very well higher than 1, in fact, the ideal phi range is around 2 to 4. So this is a soot formation range. Okay, based on the experiments, people have observed that in this range of phi, the soot levels are high. Soot formation levels are high. Since we have operating phi range of SI engines well below this 2 to 4, and also since the mixture is homogeneous inside the cylinder, okay, it won't reach this level, 2 to 4 level. That's why PM emissions are negligible. In fact, there is no particulate emission from conventional spark ignited engine. You know, in the recent development, we have GDI, gasoline direct injection. If you directly inject fuel into the cylinder in SI engine, similar to CA engine, you may have particulate emission. Particulate emissions are observed in SI engine only in GDA, which is gasoline direct injection engines. Conventional spark ignited engine with poured fuel injection don't have particulate emission, primarily because the mixture is homogeneous. In GDA, you will have heterogeneous, some heterogeneity will be there. So you will end up in getting 2 to 4 regions which forms particulate. In conventional port injected SI engine, you have longer time for mixing, fuel air mixing. So you have a homogeneous mixture with well below 2 phi range. That's why you don't have particulate emissions. So when you look at CI engine, what are the major pollutants and what are the typical concentration? NOx is one of the major pollutant from compression ignited engine, diesel engine, wherein you have NO and NO2 similar to SI engine. But the difference here is you could see that the NO2 level will be as high as 30%. It starts from 10%, it may go up to 30%. So it's very high as compared to SI engine. In fact, it's 10 times higher compared to SI engine NO2 level. As I said, later on I will discuss why it is high in CI engine and it is not high in SI engine NO2 levels. But here just take a note that you have NOx, one of the major pollutant, with NO2 levels high up to 30%. And the overall NOx concentration is around 20 gram per kg of fuel, same as we discussed for SI engine. SC is not a major pollutant from CI engine. Its level is much lower than SI engine. SC levels are much lower than SI engine. In fact, it is lower by a factor of 5 times lower than SI engine. What could be the possible reason?
Typically, leaner mixtures are used.
Yeah, so more complete combustion. SC is due to incomplete combustion. Since we use up to 30 to 50% excess air, you have more air available in the cylinder. So incomplete combustion is prevented. SC is less by a factor of 5 in CI engine compared to SI engine. Similar to that, CO is also not significant from diesel engine. CO levels are much lower primarily. So these two are primarily due to excess air. Excess air causing complete combustion. Of course, you will have particulate emissions from diesel engine. Particulate emissions are significantly high, similar to NOx. Why particulate matter is emitted from diesel engine?
Heterogeneous.
Okay, the primary cause is heterogeneous mixture. So although we say Phi less than 1 lean operation in diesel engine, okay, lean operation in diesel engine, Phi less than 1, and this Phi, you know, it's a global value. And so overall, global or overall equivalence ratio is less than 1. Generally, Phi value is around 0.4 to 0.8. This is the operating Phi range. For a CI engine, diesel engine, irrespective of engine type, smaller or larger. We already discussed that it's most versatile IC engine, 3 kilowatt to 30,000 kilowatt is the typical power rating. And irrespective of small engine or large engine, this is operating Phi range, 0.4 to 0.8, well below 1. So mean that you are subjecting it to lean operation, but this is global value. Since the mixture is heterogeneous, heterogeneous mixture is primarily because you have very little time for mixing. You introduce fuel directly into engine cylinder during the later part of compression stroke. So the time available for mixing, fuel or mixing or pre-mixing before the combustion gets started is very limited. Typical injection timing, what is the typical injection timing?
Milliseconds, sir.
No, timing, injection timing in crank angle. When do you inject fuel in a diesel?
At the end of compression, at the end of compression stroke.
Any angle, any typical injection timing angle?
Maybe 10 degrees before TDC.
10 degree, generally it is around 20 degree. Okay. Sometimes it is also late 10 degree as you said. So, and as soon as you inject with a very small ignition delay time, very short ignition delay time, we already discussed this in the first module. After you are injecting almost end of compression stroke, you are injecting fuel, okay, 10 or 20 degrees, which is almost nearer to TDC. And with a very small time lag, ignition delay time, combustion gets started. So the time available for mixing is few degree crank angle. This is the reason why we have this heterogeneous fuel air mixture. This heterogeneous fuel air mixture result in local fuel air ratio, equivalence ratio, varying from 0 to infinite. 0 is only air and infinite is only fuel. So you have regions in the combustion chamber with all possible combinations of E anywhere between 0 to infinite. Because of this heterogeneity, mixture heterogeneity, you have a non-uniform mixture distribution in diesel engine. Okay, so inside the cylinder, if you look at, you will very well have regions with Phi around 2 to 4. You have this Phi 2 to 4 regions available inside the combustion chamber. Okay, and this is causing the soot, which is a major component of particulate matter. So particulate matter emissions are significantly high in diesel engine because of this heterogeneous mixture, causing local fuel-rich region, resulting in solid carbon, which is soot formation. Soot is nothing but solid carbon. Okay, C9, C10, something around that. So it's basically a carbon particle that we call it as soot, and this is formed with a very rich fuel-rich. Okay, fuel-rich regions, and above all, so the major pollutant from diesel engines are NOx and particulate. Okay, these two are the major pollutant, and above all, you might have come across this NOx PM trade-off. What is NOx PM trade-off?
The conditions which favor lesser NOx emissions will result in more PM and so on. So we'll have to somehow have a point which satisfies both the limits.
Getting nitrogen neutral gas requires high temperature, wherein that production of your this particulate matter is dependent on high temperature. So it is vice versa.
So there is the trade-off is, you can look at this plot, which shows NOx in y-axis and particulate emissions in x-axis. So you have a trend something like this. Now, when you try to reduce, suppose you have a high NOx level in the engine cylinder, you want to reduce the NOx. Okay, so you adapt some strategy. So you are following this direction. Okay, So finally, you are reaching here. So you are reaching a point where NOx levels are significantly reduced from a high level to low level. But initially, you have a PM, particulate matter, very low, right? You are here. Now, after reducing NOx, you see that you are here, okay? So you could see that the particulate emissions are significantly increased. After you reduce NOx to a lower level, you could observe that the particulate values are significantly increased. Now, if you suppose you get a high particulate emission, you want to reduce it. You adopt some strategy, right? So you are now you are moving in this direction, opposite direction. So you have a high PM, you want to reduce it. You are adopting some strategy. So you are moving in this direction. You end up here. You have reduced particulate emission, but you resulted in high. The strategy that you adopted resulted in high NOx. So this is true for whatever strategy you adopt. Later on, we are going to discuss about the different NOx and particulate control strategies, pollutant control strategies we are going to discuss. For all the 4 regulated pollutant, we are going to discuss the strategies for controlling NOx and PM. There are different strategies available to control NOx and to control PM. So whatever strategy you adopt, whatever may be the type of strategy you adopt, if you reduce NOx, you are going to end up in producing very high particulate values. If you reduce PM by using any strategy, available strategy, you are going to end up in producing very high NOx level. Okay, so you always, this is what is a classic NOx PM trade-off in conventional diesel combustion, right? So you have 2 major pollutant, NOx and PM, and you have a trade-off between these 2 pollutant, meaning you cannot simultaneously reduce NOx and PM to very low level by adopting any in-cylinder strategy. Later on, I will discuss about these strategies to control pollutants. Just take a note here that because of this trade-off, you won't be able to reduce these 2 pollutants simultaneously to very low level. Then how we take care? How we meet the emission mandates?
After using some secondary treatment to the exhaust gas.
Yeah, it's after treatment. Okay, I will also discuss about those strategies. So the general practice is you will be able to control one of the pollutant in the cylinder, and the other pollutant is generally reduced in the tailpipe by using some external device. It's called after treatment device. So only by using after treatment device, you will be able to meet the emission mandate. Okay, this is one of the problem with the diesel engine, current diesel engine subjected to conventional diesel combustion. You have this trade-off, so you have to invest more to control this NOx and PM because of this trade-off, as you cannot reduce these 2 pollutants simultaneously inside the cylinder. This is one of the inherent problem with the diesel engine. Later on, I will discuss about how we can simultaneously reduce these 2 pollutants. This is one of the research area I am currently focusing on. Right, so we could reduce NOx and PM to near 0 level by adopting a different combustion strategy. It is not possible in conventional combustion strategy. We have adopted a different combustion strategy, and we could simultaneously bring down NOx and PM to almost 0 level, which is impossible in conventional combustion. Later on in the emission control or pollutant control chapter, I will discuss about those strategies. Clear?
Clear, sir. So you are doing research on this, sir?
Yes.
Okay, sir.
My current focus area is running diesel engine in alternative combustion mode to bring near 0 levels of NOx and PM.
Thank you, sir.
Okay. So we have just now discussed the different pollutants, okay, from spark ignited and compression ignited engine. Typical concentration of these pollutants are also discussed. So in SI engine, you have 3 pollutants, primary pollutants. NOx, in that NO is a major component. Then you have unburned hydrocarbon, carbon monoxide. In CI engine, you have NOx. In NOx, you have both NO and NO2. NO2 concentration may go up to 30%. You will have CO and HC very low level because of excess air. But particulate emissions are there, and there is a trade-off between NOx and particulate. So in CI engine, you have 4 major pollutants, NOx, CO, HC, and particulate, and there is a trade-off between NOx and PM. So we can say that it is more challenging to control pollutant from diesel engine rather than SI engine. So with that understanding, now I will briefly talk about what are the health effects of these four species. Since they are designated as criteria pollutants or primary pollutants, we should look at what are the effects these four species create on the human health. Okay, and that provides the premise for why we need to invest more to reduce the concentration of these pollutants.
Sir, I have a question. Can I ask if you allow, please?
Yeah, yes.
So basically, SI engines also have NOx emission, right, sir? And you have told
Yes,
that
yes.
NO is the majority in the pollutant formation, whereas diesel engine is also having NOx, like what I would say, emission quite high. And that NOx, NO2 is the major pollutant, right, sir?
No. NO is a major component, both in SA and CI.
Okay, sir.
What I said is in SA engine, NO is around 97%. NO2 is only 3% or less than that. It's negligible.
Right.
Diesel engine, NO2 is 10 to 30%. The remaining is NO. So meaning you have NO varying from 70 to 90%.
Thank you, sir. Sir, one question I want to ask is like for the same cc of engine, like if I assume that both are 500 cc, the pollution, the level of emission for the NOx will be higher in SI or CI?
It is same, of the same order. That's what I said.
Okay.
NOx level for the same rating, power rating, yes, you need to do a fair comparison. If you do a fair comparison with a similar power rating, the NOx levels are almost same, total NOx. In the total NOx, NO and NO2 levels will be different for the two engine category, but total value of NOx will be almost of the same order.
So the reason I'm asking this question to you is basically, sir, you have taught us that the average operating temperature of SI engine is quite higher than the CI engine because of rich fuel mixture, if I'm not wrong. And somewhere we have read that the NOx is the function of temperature that the combustion chamber sees. So if the combustion chamber temperature is higher in what I mean to say SI engine, why the both engine is ending up with producing the same level of NOx?
It's a good observation. The answer to that is you have a non-uniform mixture distribution in diesel engine. SI engine, everywhere you have a uniform P, you have a uniform T. But in CI engine, you have overall is lean. Okay, you have excess air. But what is also happening because of non-uniform mixture distribution, locally you have rich. That is the reason why you are forming soot. So locally you will have all possible combination of Phi and T. Okay, emission pollutants are found due to local values of Phi and T rather than global. Though you have an overall lean, overall lower temperature, average temperature is less. Okay, locally you will have a temperature spike. That is enough to create the kinetics, NO kinetics.
Oh, okay, sir. Thank you so
Local
much.
spikes, temperature spikes will be there. That will lead to NO formation.
Thank you, sir. Thank you so much.
Average temperature will be much lower in diesel engine compared to SI engine. But other thing you need to note down here is, though you have excess air, compression ratio is almost double, even for the same power rating. Okay, so
Right.
that will create that local temperature spike which cause NO.
Thank you, sir. Thank you so much. Clear now.
Yeah. Okay, so now let us look at the health effects of these pollutants, primary pollutants. Okay, so the first one, one of the major species, I mean the species that cause health effects is carbon monoxide. You know, this gas, carbon monoxide, is well known to you as a toxic gas. Okay, it's a poisonous gas. You know that. So carbon monoxide is emitted from IC engine due to incomplete combustion. Any oxygen deficiency during combustion of fuel air mixture, okay, will lead to forming this CO. And CO is a well-known toxic gas, poisonous gas. Okay, so the problem that carbon monoxide will create is once you inhale this exhaust gas, primarily, so you have to be careful when you are standing, when you are parking or stopping your vehicle momentarily in front of the signals. Okay, so we have a lot of signal, we stop and go, especially in city driving. So once you inhale this exhaust gas emitted from vehicles having IC engine, Okay, so it is more likely that you take in these species CO inside. The problem with CO is it has a very high affinity to hemoglobin. You know what is hemoglobin? Okay, it carries oxygen. Hemoglobin functions to carry oxygen to cells and tissues. Okay, in the blood you have this hemoglobin, and through this you are transferring oxygen to the cells and tissues. Okay, cells and tissues need oxygen for the regular functioning. Once you inhale exhaust gas, engine exhaust gas along with CO has very high affinity to hemoglobin. It can combine with hemoglobin and form this carboxyhemoglobin. Okay, so once it goes and occupies, in fact, it is said to be having 200 times higher affinity to hemoglobin than oxygen. Compared to oxygen, CO has a very high affinity to hemoglobin. So it can very well combine with hemoglobin and form this carboxyhemoglobin. Once it forms carboxyhemoglobin, the space is not available for oxygen. Okay, so what will happen because of the formation of carboxyhemoglobin? Your cells and tissues will be deprived of oxygen, so it will damage the cells and tissues. Okay, so the cells and tissues need oxygen for the regular functioning, continuous functioning. Once you have CO inhaled through your respiratory system, it reacts with the hemoglobin in the blood and form carboxyhemoglobin. It reduces oxygen carrying capacity of the blood. Okay, and due to which cells and tissues, our body cells and tissues will be deprived of oxygen, and this will eventually damage cells and tissues. And one of the organ that is on high oxygen demand is, which organ is on high oxygen demand?
So lungs.
No, lungs is what is
Liver.
Heart.
what is that?
Heart, sir.
Brain.
Brain also, yes. So
Brain. So brain and nervous system, our entire nervous system is on high oxygen demand. Okay, so once you have this carboxyhemoglobin, brain is also deprived of oxygen. So what mechanism we have once you have oxygen deficiency?
sir, if we have this thing,
If our body has oxygen deficiency, we have an automated mechanism. What is that?
we have to breathe very fast actually in that.
Yawn.
Yeah, you have to yawn, right? So when you yawn, you are actually taking in more oxygen because the body is in high demand for oxygen. That is one of the signals that your body has less oxygen when you start yawning often. Okay, so our nervous system, especially brain, is in high oxygen demand. Once this hemoglobin contains less oxygen, once it contains this carboxyhemoglobin, the oxygen supply to brain is reduced gradually. One of the immediate effect of this reduced oxygen supply to brain and nervous system is there is no proper coordination between brain and the body organs. So your organ will start dysfunctioning. Okay, it won't do its, signal is coming from the brain to all the organs. Once you have a oxygen deficiency to the brain, okay, the effect will be more severe than you think. There will be lack of coordination between brain and the body organ. Brain won't function properly or won't send the signal properly. So there will be lack of coordination between brain and the body organ. The effect of all this will be there will be rapid breathing, especially when the concentration, there is a threshold limit for all this. It will be under control as long as the concentration of CO is very low. Once it reaches a threshold level or above it, you will feel this rapid breathing. This is one of the symptoms. And the worst case scenario is cardiac arrest. You will lose consciousness. CO levels, if they are high above the threshold value, there will be rapid breathing followed by cardiac arrest. The heart will stop functioning. You will lose consciousness. Okay, so this is the effect of CO. It's more dangerous than we think. Okay, and until otherwise it is at a very low level, it can create any kind of effect, including fatal. The second one is oxides of nitrogen, which has NO and NO2. Okay, among these two, we need to look at the effect of both NO and NO2. The NO2 is more dangerous because it has a very low solubility, right? If it is soluble, the problem is it can be soluble in the mucus, in the nose, or in the throat lining. Okay, we have it may get dissolved. Once it dissolves, it forms, of course, acids, nitric or nitrous acids, both NO and NO2. Once it get dissolved in the mucus, it forms acid. You know what effect an acid can create. Okay, so it will create immediate effect is irritation. Okay. And then once it penetrate deep into lungs, it is known to cause asthma, NO2 or NO. Once it goes deeper into lungs, it can create asthma. Similar to CO, it also has affinity to hemoglobin. It reduces oxygen carrying capacity of the blood, and it is also known to destroy RBC, red blood corpuscles. Okay, so it is important for our regular body functioning. So it reduces oxygen level, it destroys this RBC. One of the symptoms of high NO or NO2 level in the body is the skin turns out to be blue in color. Okay, so again there is a threshold limit. Until that threshold limit is reached, you don't have any effect. But once you take in more NO or NO2, you will have these effects. Unbound hydrocarbon. So unbound hydrocarbon is not one species like CO. I already said that you have more than 100 species coming out of the engine exhaust. It's a multi-component species, unbound hydrocarbon. Any partially oxidized or unoxidized fuel, okay, will become this unbound hydrocarbon. So you have typically more than 150 species, okay, as indicated here, put together as unbound hydrocarbon. And the problem is not all these species are safe. Any species which has a benzene ring, right? So I already said about this. This benzene ring based species have the potential to cause cancer, okay, carcinogenic. And more severe effect will be with PAH. PAH is polyaromatic hydrocarbon. So you will have more than one benzene ring. This is a typical molecular structure of PAH. This is polyaromatic hydrocarbon. This polyaromatic hydrocarbon, they have a potential to cause cancer. So once unbound hydrocarbon are taken in, out of this 150 species, you also have this aromatic benzene ring-like structure, one ring or two ring, right? You also have multi-rings, okay, designated as polyaromatic, more than one aromatic ring structure. Okay, once this species goes in, they are going to create cancer, okay? Once you inhale exhaust along with these species, they have a potential to cause cancer. So these are the designated toxic species, benzene and also butadiene. So it's one of the hydrocarbon. All these are hydrocarbon, okay. Depending on the molecular structure, their severity on health effects is going to be dependent on. Particulate matter or simply particulates, okay. It's a complex multi-component mixture of solid, liquid and gas-based matter. All three states of matter put together is particulate matter. I will talk more about its composition later on, but here our focus is to see what health effects it can create. So particulate matter has all three states of matter, and the most important thing is soot, solid particles, okay, carbon particles are soot, and almost 50% of particulate is soot. Okay, and you know the settling time of these particles, solid particle, is inversely proportional to the diameter. In fact, it's inversely proportional to the square of the diameter. So there is something called settling time. It's inversely proportional to square of the diameter of the particle. Okay, so what problem this creates? This relationship, right, shows that there is a problem. What is that you have noticed? Settling time of particle on the ground is inversely proportional to square of the particle diameter.
So smaller the diameter of the particle, it will take more time to settle.
To settle down, exactly. Smaller the diameter, more the time it takes to settle down on the ground. Unfortunately, more than 90% of the diesel exhaust is with 2.5 micron 10 to minus 6 meter. Okay, so more than 90% of diesel particulates are having size, particle size, okay, less than this 2.5 micron. So you have more smaller size particles emitted from diesel engine with size less than 2.5 micron, okay, and they take more time to settle down on the ground, meaning they are suspended in the ambient, surrounding ambient for a longer period of time. Since these particles are suspended in surrounding ambient for a longer period of time, the problem is the chances of you taking in the particle through your respiratory system is high. So you have particle suspended in air. When once you breathe in, you take air along with this particle. Since these particles are suspended for a longer period of time in the air. Okay, so smaller size particle can penetrate deep into lungs. Smaller size particle can penetrate deep into lungs. So you have this smaller size particle going deep into lung. The problem is these particles are coated, these particles on the surface, they are coated with the hydrocarbon species. And the probability of PAH, polyaromatic hydrocarbon, okay, so this is soot, right, provides a surface for this liquid phase polyaromatic hydrocarbon to go and get adsorbed. You have a surface, particle surface, and in that surface, the liquid phase polyaromatic hydrocarbon can go and get adsorbed. You know what an adsorption is, it's a surface phenomena. So this will get deposited, or in fact, you can say that the particles are coated with PAH. Once you inhale air containing this particle along with PAH, you can imagine what damage it creates on the human health. Okay, so you are taking in air. In the air, you have small size particle, and these particles are coated because these particles are emitted from the engine tailpipe, right? So in the tailpipe, you have this particle emerging out. PAH also emerges out. It is likely that this particle get coated with PAH. Okay. The problem is you don't know what air you are taking in, right, through your respiratory system, whether it is a clean particle or a particle coated with PAH, you don't know. Okay, you cannot predict that. So once you take this particle along with the coated PAH, it goes deeper, especially smaller size particle, it goes deeper into lungs and it causes lung cancer. In fact, in metropolitan cities, especially cities like Delhi, they have a lot of problem with lung cancer. The number of people infected with lung cancer has increased more severely in the recent time. That's why diesel-based vehicles are banned in some of the cities, including Delhi. They go more with CNG. You might have heard about this, right? So, which is having less severe effects. Okay. So lung cancer is a problem in metropolitan cities, including Delhi. The levels are very high. I mean, airborne particles coated with PAH, the levels are high. So the chances of people getting infected with lung cancer is very high in metropolitan cities. This is the damage this particulate can cause on the human health. So you could notice that all the four species can cause fatal effects on the human health. Some of them are immediate effect and some of them are long-term effect. You don't know because you know that lung is a unidirectional valve. Whatever you takes in, it cannot come out. Okay, once it goes, get deposited forever throughout your life cycle. Okay, so the problem of these species getting into human being is more severe. As you could see, they can cause any damage, including fatal damage. That's why their concentration needs to be checked. As I said, there is a threshold value human body can tolerate. Once you take in beyond the threshold value, you have all these fatal effects, severe effects, as discussed now. Clear?
Clear, sir.
So we have now discussed about the health effects. I will get started with the next topic and continue in detail in the next class. So the next topic is about the sources for pollutant formation. So here we are going to look at how the pollutants are formed in SI engine and CI engine. You could see that the sources are slightly different. So we are going to look at separately for SI and CI engine. What are the sources, available sources that can create this pollutant formation? Okay. So we are going to look at how the pollutants are formed in SI and CI engine. So let us first start with the spark ignited engine. Let us look at the pollutant formation sources. Okay. So here what we are going to do is we are going to track the engine operating cycle. Okay. In a typical SI engine operating cycle, we are going to look at how these pollutants are formed, what kind of sources are involved in forming this pollutant. You know before that, you know that in SI engine, you have NO, you have unburned hydrocarbon, you have CO. These three are the primary pollutants formed in spark ignited engine. Now we are going to look at, in a typical engine operating cycle, what are the sources for forming this NO, SC and CO. It's very important to understand the sources that result in forming NO, SC and CO. That's what we are going to look at. So when I say a typical engine operating cycle, you know it includes intake, compression, combustion, expansion and exhaust. Okay, the standard processes during an engine operating cycle. We are going to look at, we are going to track when, at what time this pollutants, primary pollutants are formed in a spark ignited engine. Starting with compression, intake is not a major source for forming any of these three pollutants. During compression, there is a source. Okay, let us look at what is happening. During compression, you know, in a SI engine, you are compressing fuel-air mixture. Fuel and air mixture is compressed in a spark ignited engine. When you compress fuel-air mixture, the deposits inside the engine, I will give more detail later on. Carbon deposits are formed in a spark ignited engine. One of the sources hydrocarbons like olefins. Olefins can form higher deposits, carbon deposits inside a spark ignited engine. These deposits are of porous nature. Okay. Because of the porous nature, some hydrocarbon, unburned hydrocarbon will go. Unburned hydrocarbon here is nothing but unburned fuel. When you compress fuel-air mixture, since these deposits are of porous nature, some of the fraction of the total fuel-air mixture in the cylinder goes and get locked in the deposits. Okay, and then you have oil layers in the engine cylinder. Okay, you will have lubricating oil layers, especially in the components like piston and liner, wherein you need a boundary lubrication system to reduce the wear and tear. You will have a film, oil film. Okay, wherever you have a component with very close tolerance and which moves continuously, for example piston and liner. So you will have oil layers inside the engine, and you will have this deposits, carbon deposits inside the engine. So here you have oil layers will be there, and then some of the deposits. This deposit concentration will be high when you run the engine for a longer period of time. So when you run for a longer duration of engine, if you open the engine piston and cylinder, you could see that blackish deposits, which are nothing but carbon deposits. Okay, they are of porous nature. So what this will do is you have fuel and air. When the piston moves up during compression, you are compressing the fuel-air mixture. So you have fuel-air mixture being compressed by the piston upward movement. And since you have pores, deposits here which are of porous nature, some fraction of the fuel will go and get locked in the pores. Similarly, a fraction of fuel will go and get adsorbed on the oil layers. Okay, so this process is called adsorption. What is adsorption? Difference between adsorption and absorption?
One is a surface level phenomenon and other is a volumetric.
Bulk
Phenomenon, yeah.
So adsorption is a surface phenomenon. Okay, so this a fraction of fuel-air mixture will go and get adsorbed on the surface. This oil surface as well as this carbon deposit, okay, porous carbon deposit. It will lock. You can say that fraction of fuel-air mixture is locked in the oil layer as well as in the deposits. Okay, so this is what is happening when the piston is moving up during the compression stroke. That is what is indicated here. You have carbon deposits and oil layer adsorb this hydrocarbon, unburned hydrocarbon or a fraction of fuel. And then you have a crevice flow. Crevice flow we have already discussed. You have a radial clearance between the piston outer surface and the, so here you have 3 rings, okay, in the piston. on either side. So you have a FLR mixture going, a fraction of FLR mixture going into this, because here you have a higher pressure when the piston moves up. The pressure is low here. Okay, the pressure is low here. The pressure is high in the cylinder. This differential pressure will drive the flow of FLR mixture from the cylinder region to the crevice region. This is what is meant by crevice flow. In fact, this is one of the major source for unbound emission. I will talk more about it later on. So a considerable fraction of FLR mixture goes and get locked in the crevice. Okay, the problem is this surfaces, I mean the oil layer and carbon deposit that absorb fuel, or the fuel that goes into the crevice, flame cannot reach in this region. You know, in SI engine, the flame has to ignite the mixture, FLR mixture. So fuel goes and get locked in the carbon deposits or in an oil layer or in a crevice, the flame cannot reach this oil layer. I mean, the flame cannot reach the fuel locked in an oil layer or a carbon deposit or a crevice. So it means they cannot, the flame cannot burn the fuel that is locked in these regions, oil layer region or carbon deposit region or crevice region. Okay, thus it will become one of the major source for unbound emission. Okay, so I stop here. It's time up. I will continue this in the next class. If you have any questions, I can take. Are there any doubts?
No, sir.
Okay.
Sir, today Hemant is not well, that is why he is not attending the class, sir.
Okay, I have noted down.
Right, sir.
Okay, see you tomorrow at 6 o'clock. Thank you.
Thank you so much, sir.
Thank you, sir.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you.